So the last change we're going to look at, sort of changes that we can apply to a system in equilibrium, is temperature. So we've done concentration and pressure. We're going to just do temperature now. There's a few key words that we need to look at before we can get started, and they kind of are a bit tricky to get around the right way, but the good thing is we're going to look at these over and over and over again and again in our 2.4 topic, so by the end of the year these words will be really easy for you to use and recognize, so don't stress too much. Okay, so the first kind of concept we're going to look at is that in order to break a bond between two particles, for example, if I've got a water particle, H2O, and I want to break the bond between hydrogen and oxygen, that requires energy. So energy must be supplied to break bonds. On the other hand, when we reform new bonds, so maybe we break these bonds and then the hydrogen and the hydrogen bond together to form hydrogen gas, when we make that new bond, this one here, we're going to release energy. So if we look at overall the energy that has to go in to break bonds versus the energy that comes out once we make the bonds in the product, if we get more energy coming out than we had to put in, then we say a reaction is exothermic. If I have to put in more energy than what I actually get out, then my reaction is endothermic. So let's have a look at that. You would have seen these diagrams in our part A. We looked at this one actually. So we looked at the energy of the reactants versus the energy of the product. So we looked at the activation energy as that kind of hill that we've got to get over for a collision to actually be successful. Now if we look at the difference between the energy of reactants and the energy of products, we've got a gap of about this much. So if our products are at a lower energy than our reactants, then we've released energy to get down there. So that's exothermic, so we've got more energy coming out than we actually had to put in. On the other hand, an endothermic reaction, I have got my energy of reactants and energy of products. Again, I've got my activation energy to have a successful collision. If I look at the difference between reactants to products, overall, I've had to absorb some energy to get there. So this is endothermic. The energy supplied to break those bonds was more than the energy given out when we made new bonds. So if a reaction is exothermic, we are giving more energy out than we have to put in. So we can say that on the whole, heat exits the reaction. Exothermic exits. Okay, think that in your head. Heat will exit the reaction if there's heat coming out. Endothermic, I have to put more in than I actually get out. So as a whole, heat energy has to enter the reaction. So endo, enter, exo, exits. Okay, and we're talking about heat energy here. So let's think about this now. Think to yourself, how would this reaction vessel feel? So if I'm having more energy coming out than having to be put in, you should be thinking to yourself, this would feel quite hot to the touch, okay, because heat energy is coming out, more so than it had to be taken in. On the other hand, endothermic, I'm having to put more energy in than I'm getting out, so this will feel cold. And the reason for that is because I am having to take energy from my heat, from my warmth, and from the warmth of the air around into the reaction to be used for that bond breaking. So my heat energy is being changed into breaking those bonds between the reactants. Okay, so this will feel cold. So we've got our vocab here. And just as a reminder, so we're going to have one reaction direction will be exothermic, and always is the case, the opposite will be endothermic. So forwards reaction is exo, backwards would be endo, and vice versa. Okay, so some more kind of information that we need is this thing that is delta RH. Okay, so delta remember means change in. Think back to your year 10 forces in motion. This is the heat energy or the enthalpy of the forward reaction. So really importantly, highlight that in your notes. Delta RH gives us information of the forward reaction. And therefore, because we know that whatever forwards is, backwards is opposite, we've also got that information. But that delta RH is referring to the forwards direction. If it's negative, so if delta RH is a negative number, then the forwards direction is exothermic. Remember, exo, heat exits, heat is given out to the surroundings. If it's positive, then forwards direction is endothermic. The forwards reaction takes heat in from the surrounds and makes the surrounds feel cold because it's taking away the heat from the surrounds. Okay, so let's keep that in mind now. Okay, so if we increase the temperature of a system, the system will respond to decrease the temperature, right? We want to minimize the change. Now let's think, how would the system decrease the temperature? Okay, so it's going to favor the endothermic direction that will take away that added heat. It will use it up in that reaction direction. Okay, so if we look here, we're looking for the reaction direction where delta RH is positive because that tells us that's the endothermic way. Okay, so delta RH tells us which way is endo, which way is exo, so that we know, because it's different for every reaction. So in this case here, my delta RH is negative 92 kilojoules per mole. So that's telling me in the forwards direction, turning nitrogen and hydrogen into those 2 moles of ammonia, I am giving out heat. Okay, exothermic is the negative. So negative tells me it's exothermic in the forward direction. So that tells me if forwards is exo, backwards must be endo. Okay, so we've got backwards is endothermic, will absorb that added heat. So if I increase the temperature, equilibrium would shift to minimize the effects of that change, and it will favor the endothermic direction, which in this case is backwards, to reduce the temperature. Putting the link in here, that will decrease the amount of NH3 because it's favoring the backwards direction to use it up. On the other hand, if the temperature was decreased, so I cooled it down, maybe I put this in a bath of ice, the reaction will shift in the exothermic direction because exothermic means heat given out. It will warm itself back up, warm itself up in the surroundings. And in this case only, exothermic is forwards, and I know that because delta RH is negative, telling me that forwards is exothermic. So if I decrease the temperature, I'll favor exothermic to minimize the effects of that cooling by making more heat energy and giving it out. Heat exits, exothermic. So here's a bit of a summary for this. I tried to make it as simple as possible in here because this is a really tricky concept. So if I increase the temperature of my system, okay, remember, if I increase the temperature, the generic statement applies, okay, don't get overwhelmed. Go step by step through this list every single time. The system responds to minimize the change, and it's going to do this by decreasing the temperature again. How is it going to decrease the temperature though? Okay, so we've got the achieved level of saying the system responds to minimize the change by decreasing the temperature. How does it do this though for that merit and excellence? We need all these steps. It does this by favoring the endothermic direction. Okay, because this uses up that added heat energy. It takes it in. Endo. Heat enters into the reaction. Okay, it takes it away from the surroundings into the reaction. And remember, we have to look at the specific example, and we'll know which way is endothermic because we'll know by looking at the delta RH. Is it negative for forwards or is it positive for forwards? Okay, alternatively, if we decreased the temperature of the system, the system would respond to minimize the change by increasing the temperature again. And it's going to do this by favoring the exothermic direction, so that heat will exit from the reaction into the surrounding environment to warm it back up. Okay, so the reaction itself is the provider of the heat, or the providing means to get rid of the heat that was just added. So remember, exothermic is the direction which has the negative sign, so we're going to favor that direction if we decrease the temperature to try and make more heat energy to warm it back up. I've got a reminder down here. The delta RH is telling us the information for the forwards direction. And remember to link all your explanation to the actual question. Does this mean you'd get more product, less product? What's the color change? What was the kind of observations that we'll see? Which you'd get given in the question. You'll just have to link back to it. Okay, now really importantly is that the value of Kc does change with temperature. So when we looked at pressure and concentration, Kc didn't change because we ended up with the same ratio of products and reactants. That's not going to be the case with temperature. So if we have a look at the following example here, I've got Kc is 4.0 times 10 to the power of 31 when it's 300 degrees Celsius. And if I increase my temperature up to 500 degrees Celsius, my Kc drops down to 4 times 10 to the power of 18. So what this is telling me is that, so we'll go through this here and then we'll do another example, is that at a higher temperature, Kc is smaller. So that's the first point that we need to note, is that Kc dropped. Remember, Kc is products over reactants concentration. So if Kc is a smaller number, that means there's less product and more reactant at that 500 degrees. So Kc dropping, that's the first bit of information I can get, is there is going to be less product. So something's happening here where the reverse reaction is being favored because I'm making less product. I'm going to the reactant side. So what we can establish here is increasing the temperature decreased the amount of product. In this example only, we have to look at each one of these example by example. So we're establishing here that equilibrium has moved in the backwards direction to make more reactants. That's what Kc has told me. We also know that we increased the temperature. We went from 300 to 500. And from what we just looked at, an increase in temperature favors the endothermic direction so that heat will enter the reaction from the surroundings and cool the surroundings back down. It'll use up all that added heat energy. So what we can conclude, we have to put these two pieces of information together. Now this is what we're always going to do with temperature questions. By looking at Kc, we've established that the backwards direction is favored. We also know generically that an increase in temperature favors endothermic. So what we can conclude for this reaction is that backwards is endothermic because it was favored when the temperature got higher. So what does that mean the forwards is? Well, it must be the opposite. Must be exothermic. Really importantly, don't get confused with the effect of temperature on the rate of reaction. When I increase the temperature, the rate of the forwards and the rate of reverse will increase proportionally. They'll increase the same amount. Okay, so we're not talking about rate here at all. Make sure you're getting the question right. So let's have a go at this question here regarding temperature changes. Okay, so we've got this reaction here, SO2 plus oxygen going to sulfur trioxide. So, when the reaction is carried out at 450 degrees, Kc value is higher than the value at 600 degrees. Okay, there's a whole lot of words here, a whole lot of information. I'm just going to write this down in a way that makes a bit more sense to me. So, at 450 degrees, that is where I was at, and I also go to 600 degrees. Now, Kc is higher at 450. Yeah, so I'm just going to say, okay, so Kc is higher at 450 than it is at 600. This just makes more sense to me to kind of help me plan my answer. Justify whether the oxidation of sulfur dioxide gas, SO2, going into sulfur trioxide is exo or endothermic. So they're asking me this way, forwards, is that exothermic or is that endothermic? And all I've got is my changes in Kc. So the last time we looked at, they told us forward is exo or forward is endo by looking at the delta RH value being positive or negative. This time, they've given me the Kc information and want me to tell them about what sort of sign delta RH would have. So, let's start with what we do know. So there's 2 points that we're going to have to look through here. So when we went from 450 degrees, so we went from 600 to 450. So we're carrying it at 450. It's higher Kc than when it was at 600. So what we've got here, obviously you should put this in full sentences. I'm just going to bullet point. The temperature has decreased from 600 degrees to 450 degrees Celsius. Okay, so this is just stating the obvious. The temperature's decreased from 600 to 450 degrees. What happened to Kc? Again, just stating the obvious. Kc got larger or higher. Okay. How can I start to link these together? Since Kc is the ratio of products concentration over the ratio of reactants, if Kc got bigger, this means that at 450 degrees, more products were produced. So if you go back to the first few lessons we started on, Part B, and Kc and all of that, if you're not understanding that Kc is products concentration over reactants, this isn't going to make any sense. So you need to go back to the beginning and make sure you've really got that down. Okay, so Kc got larger. That's just the obvious information they've given me. It got higher. Me starting to kind of get to that merit level is making this inference that if Kc got higher, what that's telling me is that at 450 degrees, more products are being produced. Okay, so I'm making more products at 450 degrees than I was at 600 degrees. Okay, so it's really important I've got 2 temperatures to compare, otherwise I can't really have any information. Okay, so what's that telling me? Forwards or backwards is favoured if I'm making more products. Okay, forwards. Therefore, forwards direction is favoured as the temperature drops. So when I drop the temperature, forwards is favoured. Okay, so good to know at this point, if it's your job to make sulfur trioxide and do this reaction, you're going to want to keep cooling this reaction down to favour the forwards direction. Okay. What other information do I know? So this is what I've got about Kc. That's kind of the first part. So there's 2 parts to these temperature ones. The second kind of general information that I already know is that just generally a decrease in temperature favours exothermic direction. That is a general statement. That is not just for this reaction, it is for any reaction. If you drop the temperature, the reaction will favour the exothermic direction to produce heat to increase the temperature again. Remember, the system responds to minimize the effects of the change. So if I've decreased it from 600 to 450, my system will respond to minimize the change by increasing the temperature, which is the exothermic direction, as heat exit and is given out to warm it back up. Really importantly now, we're answering the question, is linking these two together. I know that when I decrease the temperature, exothermic is favored. What I also know in this specific example, that decreasing the temperature favored the forward direction. So putting those 2 points of information together, in this case, forward must be exothermic. Putting those 2 points together, because we have to have these 2 points of information to therefore conclude. So just like the previous example, we were given this information by looking at the delta RH being negative or positive. And then we also knew this general statement. This is the one that we should always know. And linking these 2 points together, we could explain the effects on Kc. However, this time, we're not given the delta RH. So this time we're looking at what happened to Kc, and therefore which direction is exothermic or endothermic. So as you can see for E8, we have to refer to exothermic as heat energy is being released. This is the 2019 paper, if you wanted to go back or print it out or whatever you wanted. Okay, the last bit of information is about catalysts. Catalysts don't do anything to equilibrium. And the reason for that is because, as we already looked, catalysts increase the rate of reaction, but they do this in both directions to the same extent. So because the rate of the forwards and the rate of backwards are increased the same amount, there's no change. Okay? Whereas concentration, pressure, and temperature originally increase the rate of one way until equilibrium is re-established. Except for temperature,